So keep in mind you get to drop one of your quizzes or homeworks. So I thought I'd just start by quickly going over the answers to the questions, and then maybe I'll comment on stuff. And I've got a suggestion, but I'm willing to hear some suggestions from the class as well. So the first question was on cross-validation, and I think most of the class did pretty well on this from what we've seen so far. It was about a testing and training split, and you trained on the training set, and then you evaluated on the test set, and you expect to get lower kind of error on the training because you might be overfitting onto the training data, right? So if you train specifically on a certain set of data, you expect to be lower than on a different data, and if you're going to use this to predict how well you're doing on new data, then this is going to work better on the test. I think most of the class did pretty well on this one, so I won't say too much about it. But if there are any questions about the details of it, I'm happy to take them. So Q2 was about so gradient descent, and we have some function which is decomposable. That means we can write the function in this form, right? And this is very common in learning. Anything that we're going to learn, we're usually going to have these decomposable types of functions. And I said, well, the gradient descent step is going to be times some function g of f of x, and I asked you to try and solve for this one in two cases. In the case of batch gradient descent, and in I think I said kind of incremental gradient descent at step I. Okay, and so these are kind of the two common forms, and I said the only thing we have access to, or we can compute, I can compute this. So for any one value I between 1 and n, I can compute the gradient at f of I. Okay, so I can compute this, but I want to fill this in for either batch or incremental gradient descent. And with batch gradient descent, the answer is just the sum over these functions from all the individual gradients, right? So we can decompose the gradient into, it's a linear, this linear decomposable property, so I can decompose it in terms of the sum of the individual gradients, right? And that's the point of what you can do in batch if your function is decomposable. And in the incremental step, at the ith step, then, and I think I equals to 8, then the answer was just use this one value. And that's for every value we're using a different kind of single function as a gradient. And these are the two main modes, and they're kind of the important consequences of having this decomposable property. Right, so there's some, one kind of, so I'm not sure what to say. Like, there are a bunch of people who were confused about this and wrote something like there's this least means So like update step where you have that where you can write this value as f of x times 1 x squared, or something of this form, where it was like minus, what was it? I forget, there's a minus sign, or there's a 2 in front here, something like this. So some people wrote this up, but this isn't, you know, I didn't say you have access to this. And so I think kind of it's important that you realize that often when we use gradient descent within data analysis, which is kind of the kind of one of the core ideas of this course, right? One big thing is to use gradient descent. This comes up a lot. You can decompose the function, then you can decompose the gradient, and either decompose it as, I can write the full gradient as the sum of all the terms in one step, or I can just do one term at a time. Right, so this is kind of the main idea I hope to capture in this question.
So how did you go from the g of x notation to the delta?
So the nabla. This is confusing. It's called nabla.
Sorry.
Okay, no, it's fine. Well, so you know, I just tried. I was debating how to phrase it. At some point, I left a blank here, and I said fill in the blank, or I tried to say there's some function you need to compute.
So could you like think of like the nabla as the same thing as g?
Yeah. So this is the g stood for gradient. I said there's some function that you need to compute here, and I wonder if that's what maybe that's what some of the confusion was. I said, you know, it's of this form, but I'm not telling you what this is. Figure out what this should be for each step, for the certain step. But I meant for this to be the variable that you filled in. But it's a variable function, and maybe that concept was confusing. But you're evaluating at x using this function.
So then g is the original function.
No, it's just a placeholder. It was just and maybe this was a confusion. This is not meant to represent anything in particular. It's like I almost left a question where there was kind of like just a long underscore, and fill in the blank for what to put in here.
Okay, because I think like when I took the quiz, I like thought that was like the original function, and then like when you take the gradient or like the derivative function, like you know you're taking it that. So I didn't know for a second if the g was like, you could assume that the g of f of x, like if you had some function g that the g represented like the gradient already.
Okay.
Then you could like.
So
that's what I got.
So the thought was we're trying to minimize g of f,
so, like, yeah,
and g was a function of f.
Because like on the homework, you gave us like what f of x y was.
Yeah.
And then you said for like one of the problems, like you could calculate the gradient of that function to solve the homework.
Right.
So I thought it was like similar to that. Like,
Okay. Yeah. No. I can see where that's could be confusing. Yeah. Yep. So I can. We'll take a look at it and see if what you made sense in the context of this misunderstanding. Yeah, I'm trying to write the question so that there's like a very short answer. Like I just want you to write this or just this, and I'm trying to get to that without having to a lot of ambiguity. But yeah. Any other questions about this? All right, so then the next ones were about SVD. So Q3 said I have matrix n by d, and I've run the SVD of A, and out of this I got the right singular vectors as V1, V2, up to VD, the left singular vectors U1, U2, UD here, and singular values sigma 1, sigma 2, up to sigma d, n. And then I ask you to answer 3 questions, hopefully only using these. So kind of showing the structure coming out of the CD. And okay, so I first asked for this. And there's a lot of confusion. The answer is just the second singular value. Okay, so whenever you see a norm, this is capturing a scale information. And so all the answers have to do with some form of norm. And all the scale is captured in the singular values. So it should still be the singular value. This was the left singular vector. I multiplied by it. So this kind of tells me the norm of the part of A in the direction of the left singular value. It's just this, the second one corresponds to the second. Kind of, I hadn't done this exactly in class, so thought this might be a little bit tricky. What we had done is this, where we use the right singular vector. But this is just, it's a symmetric process, and this is just the other side. So, yeah.
So, that gives you the norm of it, and then if you square that singular value, that gives you the eigenvalue for that
right
vector. So, how does that work?
Okay, so I can say sigma squared is also equal to u. I can say this. I can also say it's equal to this is also true. This is kind of what squaring is doing here. And it turns out that I can think of, I'm going to give 2 vectors here, and these vectors are going to be pointing in the same direction. So actually, this is just going to give me, this is just going to give me a scalar outside of here. But this is effectively, there's some square matrix inside here, and this ultimately is a dot product. But I can also write U transpose A transpose, and this is also here. So right, so this was this is the corresponding square matrix that corresponds with the eigenvalues, right? That's the eigenvalue sigma 2 squared, right? So if I squared, I get the eigenvalues, and now I've done this, and so U transpose A transpose, the norm of this is going to give me the eigenvalue, where this is the square matrix part of it. Yeah. So let me write the other ones up here. So for B, I asked you to write the spectral norm here, and this is max over U equals 1 of X here. Right, so is equal to this maximum over all directions. This is what the spectral norm was. And this is, again, a scale quantity. Should have to do with the singular values. And it turns out that this one is maximized at sigma 1. So this answer was just sigma 1 here. And so the spectral norm is just the top singular value. It's the direction. If I pick one direction and look at the norm just along that one direction of the data, I get the top singular value. And that's what this pulls out. And similarly, the Frobenius norm is equal to, right, remember, it's I take all the entries of A, individually I square them up, I add all those together, and then I take the square root. And this one is just going to be it's just this. That's why I put the square root in the operators. I'm just summing up all the singular values here. This is capturing all of the components, this is just capturing the top one. And these are two common properties. And so all this is captured in the singular value decomposition. And this is kind of one of the two things I want you to get out of the singular value decomposition part is that how it decomposes the matrix into the scale part and these directional parts. And then the other part, which I didn't ask you about, was about kind of how you think about the axis defining these like projections. So, I've been asked to make a practice quiz, so I made a practice quiz, but I had different questions on the practice quiz in this one. So.
On question 3, on the right-hand side of the first row, on the first question, A.
Yeah.
So it's going to be above.
This one.
So that's B. Yeah, that one's A.
On A, yeah.
On the right-hand side, where A multiplied with the vector, right? Does A have to be transposed to, or?
No, this is the proper way of so V should be a column matrix, so it's D by 1.
Okay.
And this is N by D, right? So usually you think of these, the default as a column, as a column vector. Remember, they're coming out as V transpose. It's the rows that V transpose, but the columns of V. So this is correct.
Okay.
Yeah. Whereas the left-hand side, this is an N by 1 by an N by D. So I need to do a transpose. So it's 1 by N and an N by D to make it make sense. Yeah. I think the whole idea of transpose, you have to have it to be technically correct, but it's I agree, that's always confusing. Okay, so kind of the SVD, it decomposes the kind of directional information from the scale information. And norms, we covered earlier in the semester, kind of these are scale quantities of the matrix. Right, so this is kind of linking a specific direction with a specific scale, the max single scale, and the kind of the cumulative of sort of like Pythagorean accumulation of scale, right, is what the Frobenius form is. Okay, and then the final question was on the, this is for SVD versus PCA. And so this was something I kind of mentioned offhand during the 2 lectures and that I was giving on this topic, and then it was kind of the focus of the 4th lecture when I was traveling. And principal component analysis, you don't just directly apply SVD, but you first have to center the matrix. Right, so this is the answer I was looking for. What this means is that for a matrix A, first make all columns sum to 0. And kind of the key picture you should have in mind here is that I've got some axis. This is just R2 here. But I've got some data I want to analyze that looks kind of like this. And so to analyze it with just the SVD, the first singular vector might give me something like this for V1. And this isn't really telling me the structure of the data. I want something along this axis. And so what I first do so the first thing you need to do is do a centering of the data so that I'm going to shift all of the data. So now it looks like this, and its average goes through the origin here. And now when I run SVD, it's going to give me the first direction looks like this, which is directly along kind of the main structure of the data. And so the main difference here is that you center the matrix first, you apply this operation, and then SVD gives you kind of the principal components and principal vectors. Yeah.
That red vector you just drew, that's the first right singular vector. Right?
Correct. This would be the first right singular vector. Yeah. Yeah, and the centering step is here in green. So, right. And so this is kind of a lot of times in the more general literature, not in my book, I'm careful about this, but people will conflate these two things. And if you're trying to find the best rank K subspace where K is like 10, it doesn't make that big of a difference. But when K is 1 or 2 or 3, it can make a very big difference between these two things. And you might find the first singular value is much bigger than everything else. That's really just capturing the data as not centered, not really the structure of what's going on. Okay, so I just wanted to get this out there as well. Okay, so it seems like it's a combination of, the speed of the material is probably less review than it was earlier in the semester. And we've been kind of covering a different, maybe 1 or 2 concepts every class, right? And I think sometimes maybe one of the concepts will get lost underneath one of the other ones. And so I'm still kind of building this class up, and I've tried to keep all the quiz questions distinct from previous semesters. So maybe I'm asking kind of the secondary concepts in a lot of the lectures this time, and that's what it ended up making the quiz a bit harder. But I also think all these are parts I hope you will know at the end of the semester. And so sometimes, the good news about maybe not doing as well in a quiz is that maybe it sticks in your mind a little bit, right? I should have known that next time I'm going to get it. So I'm hoping this is a chance that all of you are going to this is going to be a bit more ingrained. So, I want to make sure you learn all of this stuff. And we have one Slack lecture in the class. The plan, the last Wednesday on December 4th was going to be just a review, or I would just kind of go over stuff. And maybe this tells me this is the stuff I need to focus on in the review. We can try doing something else, right? So I think it's important. I think hopefully this helped, and I want to move on soon because this is a pretty cool lecture. But we can also spend another lecture reviewing some of this material like sooner rather than later, or we can. But otherwise, we have one more lecture on clustering after this one, and then we'll start classification, and then maybe we do it at the end. So I'm not sure. I'm open to suggestions.
I was wondering if you could find, so like when I was studying for the quiz, I read through the book, but some of the sections are kind of terse just because it's a book. But I was wondering if you could find extra readings, maybe that describe some of the things in the same way you do, because your descriptions are good, and then when I try to review them like later, I find a whole bunch of people that describe SVD in ways that are completely useless to me, or like in ways that like aren't congruent with the way that like you taught it. And so it's like kind of, you have these two different perspectives on the same linear operation happening in your head, and that's kind of juggling that to be tough.
Yeah, so if you want it the same, so, part of the reason I ended up writing out the notes, which turned into the book, is because the literature has a lots of different ways of explaining it, and the notation is different, and then you move from one concept to another, and the notation is not congruent with each other. So I tried to kind of normalize it. It's not perfect yet, but I think if you do look at the bottom of the web page, I do have a bunch of links that I used when I made this book, when I first made the notes. And those are, in principle, kind of similar in at least kind of what I was drawing on when I was making these notes. In particular, for the PCA, I forget which one this is. Yeah, so the second one, and I guess some of the links are broken now, including my own, but the second one is from some notes I took when I was in grad school that I found very helpful. And I thought it was clear, and one of the examples I kind of essentially took from these notes, but this was also one I liked. And it's buried in there, of course. And there's this No BS book. Hopefully that's still free online. It might now cost money. Oh no, there's a 360-page book online, which I thought was something that really cut out a lot of the sort of details I was less interested in when talking about linear algebra. And I don't remember exactly how that one described the SVD, but I found that book to be useful. And I think it's all on, at least some version of it's all online, so as well. So I do have those links, but if you haven't found those before, those might be useful. I've emphasized them less because my material's gotten a bit better, but they might be useful. And if you guys find a cool thing online, feel free to post it on Canvas. I know some of you have found some cool videos of stuff. Hopefully the next quiz will be kind of more back in line with the scores I'm hoping you guys will get, and you've in general been doing well in the homeworks and stuff. So I had just been remarking before class on Monday of how like the scores for the class overall have been pretty high. So on like in the aggregate. So I think I was hopeful you're in general you're picking up the material pretty well. But this is one of the reasons for having these quizzes. So, okay, so we're going to get to talk about assignment-based. So clustering, and if you remember, we're going to have some data, and for now we're going to say X is going to be a subset of our D, and I'm going to have some distance D of, say, PQ, and we're going to use the Euclidean distance between P and Q. Okay, and then we're going to have a value K, which is going to be the number of clusters. And so we're going to be given this on input in this case. Well, I'll talk a little bit about how can you kind of choose K and some challenges of that more, whether it's today or next lecture. Okay, and then we're going to make the goal more specific today than we did on Monday. We're going to find K sites, or sometimes these are called centers. S1, S2, up to Sk. And this is, again, going to be a subset of Rd, not necessarily a subset of X, so not necessarily the inputs here. And we're going to, and this is going to lead to K, so subsets, X1, x2 up to xk, and these are going to be disjoint subsets of x. As we define that xj is going to be the set of points in x such that there's this function phi of s equals sj. Okay, so it's all the points which are, their closest site is the jth site. That's the set xj. Okay, if you remember, we had some picture that looked like this, and hopefully I've got S1, S2, and S3, and so this created this, this Voronoi diagram, and these are the points. This was in X1, these are in X2, and these are in X3. And this phi function, phi of s, kind of was this mapping on the plane onto just exactly one of these sites. So it's decomposition of this set of points. Okay? All right, so this is assignment-based clustering, but now I want to say which sites are the best sites to fit. I need to somehow choose some optimization, and we're going to be focusing on the k-means version. And I'll write this up, and then I'll mention some other versions. So it means we're going to try and minimize this cost function, which is going to be sum of I equals 1 to n of the distance from xi onto phi of s squared. Right, so I'm going to look at, I want to minimize the sum of the squared errors again. Again, sum of squared errors, this is kind of the cost function we've been talking about the whole semester. So I'm minimizing the sum of these squared distances. So each point has a distance onto its assigned center. And I'm going to sum these green lines up and square them, right? And that's going to be the cost function. Right, so there's a lot going on inside of here, right? That's why we actually spent 20, 30 minutes last lecture kind of looking at this phi function. This function encodes that I'm assigning each xi onto the closest center. And then the cost is kind of defined implicitly in here of xi onto the closest center. I'll mention a bunch of other assignment-based clustering, but they all have this, they all use this mapping onto the closest center. That's how the clusters are defined in this way. They're all defined by this mapping onto the closest center. That's how I decompose my point set. There's other type of clustering that does something different, but in center-based clustering, it uses this formulation.
Have you determined like what your threshold is for points, whether or not they're considered neighbors?
There's no threshold. Right, this goes off to infinity, and a point out here, well, it's in this region by the phi function, so it gets mapped to the center. Right, there's no threshold. So this could have issues with outliers, right? And in particular, the squared distance is particularly susceptible to outliers. So this point out here will probably pull the center away from, even if there were 10 points here, it's going to shift it out towards this point. In fact, it might put one center at here. That might be the best solution. And then sharing these two clusters with another center it's probably the kind of what the optimal solution will be. Okay, so I'm not going to talk about these, but there's a couple of other cost functions. So k center is going to be equal to the max of I of xi. So it's just looking, all it cares about is the maximum possible distance. I want no point to be too far away from the center. So this can be issue with like you know, like if like no house in a city can be too far away from like a fire station. The fire station needs to be able to get there as quick as possible. I can allocate 5 fire stations. Nothing can be too far away. Maybe I end up putting more on the country part of the city district than in downtown, but that's so much. Maybe one fire station can cover all of those. And then there's the K median, which is equal to, this is again a sum over I, xi. This is not squared, right? So this is, you know, I can write it explicitly. There's a power 1 up here, right? I'm not squaring this distance. Then it's called the K-median clustering. Turns out the K-median clustering seems like more natural even, but it's much harder to actually solve for this one. This one's much harder to solve for than K-means. We'll see a pretty simple approach towards the K-means where this one becomes much, much harder to work with. There are algorithms for it nowadays, and you can do it, but it's not as simple as kind of elegant to at least get something working as with the K-means clustering. And then there's a version of this called the K-medioid, okay? And that means that the centers must be a subset of X. So the sites have to be a subset of the data. And this is actually nice when I'm not using Euclidean distance and I don't know how to kind of define things that are not a subset of the data. You can say I have a distance between airports in the US, right, based on the flight time. I don't know how to pick, you know, I can't put a center at some place which is not actually an airport. So I have to pick one of the airports. And then this version is nicer, and then there aren't any kind of clever algorithms like there are here, so I might as well use the non-squared distance. So that's why K-median. So, okay, this one has a really cool, simple algorithm as well, which is in the book, but we're not going to cover it. Okay, so we're going to focus on this K-means version. This is, you know, probably, if someone just says, I want to do clustering, you know, 6% of the time, they refer to actually this formulation. This is what they're talking about. There are 100 other formulations, and even, you know, a few others that I've mentioned, even very similar. But this is often what they're talking about. This is most commonly used. It's not always the best thing to do, but it's the most common thing to do. And it fits in with a lot of other stuff we're talking about in this course, so we're going to focus on this one. Okay. And there are 2 reasons for the squared. Why I use the squared distance here? Right. The first one is that there's going to actually be a pretty nice algorithm here, which we'll talk about, Lloyd's algorithm. But the second one is that, if you remember from the Bayesian inference point of view, when we start with Gaussian noise on data in 1D, that you end up getting, you kind of take a log and some stuff, and you get a cost function that kind of looks like this in 1D. And so this is actually pretty close to, if you're modeling each cluster as actually being a Gaussian distribution, and you're saying assign to the closest Gaussian noise around each center, and I want to model the data as fitting it with K Gaussians. It's not quite the same, and so the next lecture will focusing on the version where we're fitting a mixture of Gaussians. Okay, and that'll change a few things, but thematically and from kind of a computationally, it'll just be a more complicated version, slightly more complicated version of this, the algorithm we're going to study for this. Okay, so those are going to kind of be the 2 reasons. Okay, so any kind of structural questions on this yet? So,
I was wondering, we haven't really talked about how to find which S belongs to which group of points. We haven't mentioned that yet. Is that correct?
Well, you know, you should flip it on the head. The points belong to S, right? Think about it as S doesn't belong to, you know, each S doesn't belong to points, but the points belong to S. S is the representative of the cluster. I want to define these subsets, these K subsets, and I define them implicitly using these S's. Right? I want all the points such that their closest point is Sj.
Oh.
So that's going to be implicitly defined based on this nearest neighbor function. Right? So but this is, yeah, so I've not explained the algorithm yet, and so now I'm going to fit the pieces together, just a couple, just going to be a couple lines of code, and magically an algorithm's going to pop. Okay, so okay, and so when people refer to k-means, this is a formulation. I want to minimize this cost function. This is not an algorithm. There are many algorithms for this. The most common is called Lloyd's algorithm, and that's what we're going to talk about.
I was just wondering, so we have like this data set X. This cost function is measuring how well these subsets, this set of sites models the data. Is that right? Like, well, I guess what is this cost? Is this like a set?
Yeah. So I'm saying, yeah. So I don't have some labeled values I can use to evaluate, but I'm saying I want the data to be in kind of. I'm assuming K is the number of clusters, and I want to say there are K groups of points, and I want all the points to be close to their center the representative center of that cluster, of that group of points. And so that's one way of modeling. Every center I want to be compact. I want all the points to be somehow related to each other or close to some center. And the smaller the cost function, probably the better a job of doing that. And this is not the only cost function I can choose. These are other common cost functions. There are other ways of kind of conceptually define this without centers, right? If you take my Dayline class, you'll see another kind of handful of these notions. There's a class in the spring, which I think is, the registration is almost full, but it'll probably people just shopping on. Whole class is on clustering. There's a whole semester on different varieties of clustering, right? This is just one way of formulating it, and it's the most common one, but it's not the only. Okay, so Lloyd's algorithm. This was from Stuart Lloyd in like 1957. He was at IBM Research Lab, kind of invented this for quantizing, but he didn't publish a paper until like 15 years later because his computer got upgraded and it broke his software. He was running test stuff. And so 15 years later, like, you should really publish it. So he published it without finishing the tests. So that's kind of the fun story about this. Okay, so the first step, I'm going to admit choose somehow S subset of RD. Okay, so I'm just going to somehow initialize some set of centers. This is not going to be my final thing, but I need to start someplace. Just like in gradient descent, I initialize somewhere. We can talk about ways to initialize. Okay, and then I'm going to repeat just 2 steps. Until, so it's going to be some iterative process like gradient descent. I'm going to repeat these 2 steps until it's converged. And we'll talk about what it means to be converged. Okay, so these 2 steps are for all data points, assign x to xi, so or sj. Okay, so the first step is kind of implicit in the definition of this function, but I'm making it explicit now. Right, so I'm assigning it to one of the k different subsets. Yeah.
So when you for your initialization, S like a single site, or is it like a
S, big S, this is uppercase S here, is going to be a set of case sites. Yeah, so let me make this clear. Right, so it's going to be a set of case sites. I'm picking them somehow. Well, there are plenty of good and bad choices for how to do this. Okay, so the first one is I just use this nearest neighbor function, right, that we talked about. Okay, and then the second step is that so for all Sj, so now I'm going to kind of do some fixing of the choice of centers. I'm going to update lowercase. Okay, so I just do this simple update step where the center, right, one of these points here, is moved to the average of all the points assigned to me. This is an average of xj. Okay, so this is, I can average coordinate-wise, and it gives me all the, put that together gives me the overall average. This is, okay, and so the key reason this works is this step sets Sj equals to the arg min of P and arg D. Okay, so this averaging step minimizes the sum of the squared distances. This is the point, the average turns out to be the point which minimizes the sum of the squared distances. Right, this was true, I mentioned this before, when one dimensions, it turns out it's true in higher dimensions. And this is by the, you can show it for one dimension, then by the Pythagorean theorem, you can show it for all of the dimensions. Because the total distance decomposes along the coordinate axis. Okay? Or the squared distance decomposes along the squared distance of the coordinate axis by that Pythagorean. Right? So the squared distance gives us that the average, taking the simple average is the optimal way to place a single center with respect to the points that has been assigned. And the thing is, though, once I've done this, the assignment may change. The assignment may change, so I have to redo this assignment of which points are in which clusters. And then I have to redo where the centers are and go back and forth between these two until it's converged. All right, so pretty cool, simple algorithm. Yeah.
What about that first step, choosing some S? Is that just like randomly choosing some S?
So if you look in the notes, I say arbitrarily with a question mark. That's my question mark sound. So what is the right thing to do? A bad thing to do would be to start by choosing the subsets, right? If I choose the subsets at random, and then I do the centering step first, what's going to happen is by concentration of measure, they're all going to be about the center of the data set, and it's going to be not very good initialization. I'm better off choosing somehow the centers intelligently first. And so a pretty good, if you don't know anything else, then I would say a random subset of X is a pretty good initial heuristic. Okay, it's not perfect. If K is big enough, you're probably, and there really are K different clusters, you're probably going to end up getting 2 points in some cluster and some clusters without any points in them. And then that means you're going to have to run more iterations, and hopefully it will sort itself out. There are better ways of doing this. The textbook, and this goes into in the data mining class, there's something called the Gonzalez algorithm, and there's another thing called k-means plus plus. Okay, and so these are probably the two more formalized way of doing it. Gonzalez algorithm actually solves the k-center problem approximately, but as good as you can possibly do. And so you can use that, the input of the k-center, to here, and this is a pretty good idea. And the k-means plus plus is kind of a randomization of that. And a lot of libraries now have k-means plus plus built into it. Okay, it's but we're not going to get into it in this class. Random will do pretty good, and this is a randomized algorithm, k-means plus plus, so you might actually do either a random subset or k-means plus plus multiple times, and try running the algorithm multiple times, because you might end up starting in a bad initial configuration. And the best way out of a bad initial configuration is to throw your hands up and say, let's just start all over again. Okay? That is probably the right solution to do here, both in theory and in practice.
So we know it converges when no more updates are made. Is that right? For a given.
It's converged, yeah. So you guys are asking all the right questions. This is good. When do we know it's converged? One thing is, so one option is when no updates. Right? It could be I don't change anything between these steps. I don't reassign any points, right? And yeah, so there's no point in running it if it's not going to change the solution at all. You might go back and redo a random initialization, but no point in running the iterative part anymore. So that's true. I'm going to show hopefully later in this lecture that it eventually will have no updates, which is a nice property about the algorithm. But it won't necessarily reach the optimal solution. So we'll see that. And then this is not, so this is kind of, in theory, what you're supposed to do. In practice, it's more like gradient descent. And it could be things are moving quickly at the beginning, but if there's really a lot of data points, there might be a lot of kind of jostling around the edges. And that's not so important. So when the cost change is small. So if I can kind of keep track of what the total cost function is, maybe that might be expensive to do, but not too bad, right? It's just linear, and each of these steps is linear. So I can keep track of the cost, and if that change is pretty small, I might stop. I may not wait until it's completely stopped.
Oh, and then one other question is, we have to actually choose the amount of centers. That there's no way that we have to actually choose how many centers that we'll have.
Yep. Yeah. So the input K is part of the input for this algorithm. Yeah. So if you're not sure, run it with different Ks and see which one you like. That's kind of the short answer, and it's not too far from the long answer, which can be much longer. But that's you might run with, another option is to run with slightly more than you think, and then you'll end up getting kind of two clusters in the same, two centers close to each other, and then maybe you merge those together.
So like what happens like visually for noise? It's like it just like groups everything.
Yeah, so I was planning to kind of walk through an example on the board, and we can kind of see what happens. It's
So it like gives similarly the like does it give similarly to the key means already like solving the same problem?
to the key means already.
No, like the key means plus right. So it's like one way of solving the key.
Yeah, so this will, okay, so I can, there are two things I want to do next. I can do them in either order. One, I can kind of walk through an example. The other is I can show that every step will be decreasing this cost function. And this has the consequence that it means it will eventually converge and there will eventually be no more updates. Okay?
I think the walkthrough.
The example first, and then, yeah. Okay, so let's go through an example, and then let me try and move, Ben, wait, maybe you want to move the screen. Okay, so let me try and walk through an example here. And let me try and make it a little bit. Okay, so let's start. Maybe we'll put point over here. Okay, so this will be our starting point, and let's start with let's start with these 3 points as centers. Okay? And so I started by thinking a subset of the data points, and the next steps, they won't be a subset of the data points. Okay, so now let's see. This will induce a Voronoi diagram. Which looks like this. And this tells me the assignment of the points. Probably not what I want, right? So it means that these 4 points are going to be x1, and their average is going to be something like this. Here, these 5 points are going to be s2, and the average will probably be something like this. And these 10 points will be x3, and their average will probably be s here. Okay, let's see what happens. I actually don't know what will happen. So, okay, so I'm going to get a new Voronoi diagram here. And splits the points slightly differently. Actually, S3 has stayed the same. That's great. I don't have to calculate it again. Okay, which we use. Okay, so this will be S3. S1 is now going to move down this way. And S1 is going to be probably S1 here. And then S2 is looking good. It's going to move back up maybe here. Right? So is it clear what's happening so far?
Yeah, so like, how do you? My two questions are like, how do you know like where to draw the Voronoi diagram? And, like, how do you determine?
Yeah. So
new site?
right. So actually, what I'm doing is you won't actually draw the Voronoi diagram because in 2D you can do it, and I think I hope it helps visually kind of explain what's going on. But in practice, for every data point, I measure the distance to all the centers, and I choose the minimum. I just do it brute force. Okay, so
and then by doing that, that's how you do it.
that takes k times n time. Hopefully k is small, so if k is a constant, this is linear time still to do it. So that's okay.
Just so, like, in terms of motion, this diagram is just going to continue to turn like counterclockwise until you split up into like more intuitive clusters?
Yeah, I think the next step it'll be done.
Okay.
So how would I finish it? I'm gonna do this is now the diagram here, and purple, and so now S1, we're in the green view, and so these 5 points, this is now S1. S2 is now all of these points, and is this the same as, oh yeah, I move towards this point a little bit here. So S2, and S3 now is up S3, right? So now the Voronoi diagram looks kind of like this. But now these points are in, this is X2, this is X3, and this is X1. And I think it worked pretty well. Yeah.
Well, one thing that I was thinking about this is, so when it actually converges and it finds that center point, when it converges, it doesn't actually mean that that is the optimal center point, correct? Is that correct?
It means it's optimal with respect to that partition. With respect to the current partition it has, that's the optimal center point. But given the new center points, the optimal partition changes. Right? So,
Like the way that I'm thinking about it is like a perceptron doesn't actually find like the perfect like an SVM would find like the perfect line that separates them, like by using like supports. But this is more like a perceptron in that it would just separate them, but not necessarily find the exact center.
yeah, so this will be closer to the power method than the perceptron because it's minimizing a sum of squared errors, where perceptron essentially assumes, which we'll see in a few weeks for the rest of you, assumes there's a perfect classifier, so it just essentially measures the, it's kind of binary, it's a count-based error measurement. So this is, it's kind of like the gradient descent with the sum of the terms, right? I can essentially write this as a cost function over the coordinates of all the centers. We're kind of doing that. It's closer to the power method, but there's a lot of stuff going on at once. This is not necessarily convex. It's not guaranteed to converge to the optimal solution. Yeah.
So in the diagram and picture, where are you minimizing the cost?
Yeah, so, okay, good. So let's, we can come back and talk more about this, but let me point out that both of these steps are reducing the cost.
So together they are, or
Each step the cost goes down every time I do either step 1 or step 2, right? Right. So if I look at the cost function, I'm going to write now that the cost function as let's say as j equals 1 to k. What's the rate? Yeah, the sum of x in xj. Okay, I want to write the cost. Okay, I've just rewritten the cost function in that I've not explicitly assigned the point to the closest center here. I've just said I have some assignment. I'm going to sum over these points, and in each assignment, I'm going to measure to its center. Okay, so now if I want to look at the assignment step, let's just look at this term here with step 1. Basically what I'm doing is I'm choosing for each x here, I'm assigning it to the choice out of all the sj's which gives me the smallest value. This is exactly the cost function. So if I assign x to a different set, so I sum it up in a different kind of subset here, I assign it to a different center that reduces this term. This is one of n different terms with n data points, and this term goes down, and the other ones don't change. I'm not changing the center by itself. And then in the other set, right, in here, I'm looking at this term, and now I'm fixing xj, and I'm adjusting sj. And given just this term, there are k different ones of these, but for this purple box, the choice of sj I do reduces everything inside the purple box. And everything, the other k minus 1 terms don't change at all, so the cost decreases. So both of these steps are decreasing the overall cost function.
So then it's like, because it looks, that equation looks very similar to like the residual error.
Yep, that's right. And a lot of this class is sum of squared error stuff because it gives you these simple, beautiful kind of algorithms. Yeah. So it looks like the residual error. This is, think of the subspace approximation problem was the model was a k-dimensional subspace. Now I'm giving k points, and I'm matching onto the closest of k different points. But again, it's sum of squared errors. With regression, I'm matching only in the vertical distance, but again, sum of squared errors. In classification, you could use sum of squared errors, but turns out there are some issues with that, so we'll look at other things. But in all these, like sum of squared errors is kind of like the default way to measure error. Okay, so what are the implications of this? This means that step 1 decreases the cost, or keeps it the same if I might be close to converging, and step 2 decreases the cost. So that means every time I get to, the bottom of this loop, either the cost has, maybe it's stopped, or if the cost is decreased. Every time I start the top of the loop, I have a different implicit assignment of this set of x points are mapped into this set of xj of these partitions. This implies every kind of step, and say 1 and 2, has a distinct partition. x1, x2, up to x. Okay. Right, so I partition the points in a different way every time through. This is true because if I look at the partitions I have every time I do step 1 again, the cost is always lower than the previous time. So I can't go back to a partition I saw before because that means I would have had to have increased the cost to go back to it. And I know that can't happen. So the cost is always decreasing, so the partitions are always distinct. Even though the set of centers is infinite that I could choose, the set of partitions is finite. So it has to, at some point, stop. There could be a lot of them. It's like k to the n different different partitions I could have. I'm probably not going to see all of them, but it will converge eventually. Is the point of this. And the cost function will always decrease, so if the cost change is getting pretty small, it means I'm probably close to being done. Yep.
This may not be great as well, but I guess this cost function, we don't have we have a guarantee that it's, I guess, convex for every partition and every set of sites. Because I feel like if we don't, then we might get stuck in a certain clustering configuration. This algorithm is not going to move.
So this step by itself is convex. Right? I can choose the individual center for one center of a set of points. That's a convex problem. This isn't really, this is of a discrete sort of nature, so it's not convex. But the overall problem is not convex. It's not. This example is too cluttered, but let me draw another simple example. And there are a few more in the textbook. let's say I've got I want to assign 3 clusters onto here. The optimal is going to be S1, S2, S3. This is the optimal. But if I get in a situation where I have S1, S2, and S3, maybe I'll make these as X's in case you can't distinguish the colors. Right? This is stable, right? If I draw the Voronoi diagram here, it looks, something like this. So if I do the update step, I'm not going to change where these centers are. I'm not going to change the assignment. So it's stuck. Right? So this, if I initialize here, and there's a ways you can choose data points if you care about they come with the same sort of situation, the algorithm, Lloyd's algorithm, is not going to progress. Okay, so yeah, so this does not have nice guarantees of convex or strongly convex methods for gradient descent, or even the power method is guaranteed to converge, even though it's not convex. This one is not guaranteed to find the right solution. And so this has been kind of something people have studied. How do we fix this? Like, well, what can we possibly do? In most cases, if k is not too big, just a random subset works fine. Random restarts. Randomly restart, and at some random initialization, I will get 1 point down here and 2 up here, and this will sort itself out. Probably will happen. If I re-randomly choose the centers, I'll probably be okay. The other answer is k-means plus. K-means plus solved 2 problems. This is an algorithm. It's not too hard of an algorithm, but it's more than we're going to go into. It's a random process to choose the centers. It's not guaranteed that you will find the initial sites that are going to converge to the optimal solution, but if you do it enough times for any data set, then it will converge to the optimal solution. Okay, so it's still, you need to do this random restarts with k-means plus. But that one will eventually. There could be situations where it's actually, the optimal solution is pretty weird, where you want to pick some like outlier points, and it's very unlikely that you pick them you pick all of them in a random subset. You'd have to almost pick every different partition to get the right initialization. So the random subsets might, in some weird cases, not give you the right solution. The other issue k-means plus solved is that not only would it converge to the right solution sometimes, but one of those times would converge with a small number of steps. I said the number of possible partitions is very large, and it could be you can chain together an exponentially long set where the cost keeps decreasing, but you're not converging. And so you just run it, you're like, I'm still doing better every time I run it, but it's taking a huge number of times. And people have constructed these things. But it still might get you in that configuration, so you have to run them in parallel technically, or just at some point run it for 100 steps and then start over again. Okay, so that's the kind of from a theoretical perspective, you really know what to do, so you're gonna you can sit back and relax and not worry about things. Yeah, pre-process with k-means plus and randomly restart. And so forth, and it will pretty much solve it. The truth is, though, that the sort of scenarios that this does not work well in, I don't think anyone cares about in practice. Okay? They're going to be these really obscure things. Some of them, like the initial counterexamples, were like in really high dimensions, and there were these weird outlier points, and there weren't that many points for the number of dimensions and the size of k. If you you can put more points in there, but if you really have well-concentrated sets of points, and there really are k sets of clusters, doing a few random restarts and rerunning it is gonna work pretty well. And if you don't have that, then why are you clustering in the first place, right? Maybe you're finding out that there aren't really K-good clusters, and that's what you're doing, and you find out by running it, 5 or 10 times and say, every time I do it, it gives me back something that doesn't seem that helpful, and then, and that's what you learn, that there aren't clusters. So, I mean, there's a lot of stuff people have done to try and do something better than this, and most times you actually want to cluster. Lloyd's algorithm with random restarts will do a pretty good job, and that's why it's almost always what people use. Yeah, so we went through this pretty quick. We can talk more about this. We have another lecture on clustering where I was going to do the mixture of Gaussians, which is kind of an extension of this. And then maybe I would do a different clustering just so you show you the breadth. But we can spend more discussion on this. How do you choose K? Other sorts of issues if we want to talk about that next week. Okay, but it's a simple algorithm. It's built into sklearn in Python. I think I wrote the command in the book someplace. Yeah, so it's, or you could probably implement yourself. It's not too hard. If you want to know tricks how to implement it, you come ask me. There's some ways to store stuff in arrays, so it makes it a lot easier. Okay, so hopefully we'll the quiz is graded, and I think Ben Way said be able to upload the PDFs online so that you can see them that way as well. Okay.